Welcome back, everybody. We're going to focus on Chapter 9, which discusses hypothesis testing. And for right now, we're going to focus on Section 1. So we'll be focusing on Section 9.1. And although we're going to learn how to do our first inferential hypothesis test, specifically a z-test, where we will put together what we've learned about probability and z-scores, for this particular section, we're just going to discuss the structure of a hypothesis test. We're going to talk about the different competing hypotheses that we have in a hypothesis test, like the null and the alternative hypothesis. And then we'll talk about the difference between one-tailed and two-tailed tests. So the basic structure. Let's begin by talking about an example that will lead us to understand why hypothesis tests are necessary. Gender choice is a product that once claimed it could increase a woman's chances of having a daughter to about 80%. Even though approximately 50% of babies are boys and 50% of babies are girls. So let's say we wanted to test this, and we had a sample of 100 women using gender choice. What I want you to think about is, if gender choice does not work, how would we expect those results to look? And if you think about it, because in general half the babies born are males and half the babies are females, if gender choice did not work, we would probably expect about half of those 100 women to have female babies. If gender choice works, let's ask another question. How would the results need to look to suggest that it significantly improves the probability of having a female baby? Well, again, now if we're thinking that we would want to look and see how would the data be distributed if gender choice actually works, we'd expect to see some far departures from 50%. So we're expecting that about 50% of the babies would be females under a typical scenario. But if gender choice works, we would expect the probability of female babies to be larger than 50%. Well, we're going to be able to answer these questions about specifically what type of data we would expect to see and how differently our data would have to be from chance expectations to prove that we have statistically significant results. We're going to see how we can answer those questions via hypothesis testing. And essentially what we're doing is like putting our data on trial, because think about it, gender choice would say, hey, this product can increase the likelihood of having a female baby. And we'd say, well, where's the evidence? Where's the proof? And we say essentially the same thing when we put somebody on trial. We say that somebody is suspected of something like murder, and we'd say like, all right, well, what's the proof? Where's the evidence? So let's explore this legal analogy for a minute, because it's going to help us better understand the logic of hypothesis testing. And the reason why it's going to help us understand this logic is because it seems a little strange at first. And the reason why it seems a little strange is because, think about a court case. It starts off a little strange as well. We essentially have, whether you've thought about it this way or not, two competing hypotheses. One hypothesis is that the defendant is not guilty. And if you remember, there's always something we need to presume about people who are put on trial. We presume that they are not guilty. And doesn't that seem a little bit odd? If we've arrested someone and put them on trial for some type of crime, it seems that many people would probably think this person is guilty. But the point is, from a juror's point of view, you know nothing about this case, so you need to presume at first that this person is innocent or not guilty. Well, then we can set up some competing hypotheses. Our null hypothesis is always the hypothesis that there's no effect, no differences that we're actually seeing, and in this case that the person is innocent, that this person has committed no crime. Our alternative hypothesis would be the opposite, that the defendant is guilty. Well, in a criminal case, what we do at that point is we would collect some evidence. And we're going to do the same thing with our data, like do a research study. We'd set up some hypotheses and then we'd collect some evidence. And in the case of a legal analogy, a trial here, let's say that some witnesses saw the defendant at the crime scene and the defendant's fingerprints are also on the murder weapon. That's some pretty damning evidence for this particular person. Well, what we need to do at that point is compute the probability of finding the evidence based on our initial assumption. Remember, as a juror, you're supposed to assume that the defendant is not guilty. Then you need to say to yourself, well, what's the probability that some witnesses would see this person at the crime scene if the person is not guilty? Everything is going to be viewed through the lens of if the defendant is not guilty. So, for example, let's say the defendant's fingerprints were on the murder weapon and that evidence was presented to us. Well, what's the probability that the defendant's fingerprints would be on the murder weapon if the defendant is not guilty. Can't you see that the probability would probably be very small? So the probability is very small. It would be very unlikely that the person's fingerprints would be on the murder weapon if the defendant is not guilty. Well, so when we talk about computing that probability, we're able to do it in a criminal type of trial intuitively, like just the way we typically would think about probabilities. But now with our data, we're going to be able to compute some exact probabilities. So again, everything's being viewed through that lens of the defendant being not guilty, through our null hypothesis. And as I mentioned, it's very unlikely that we'd find this evidence if the defendant is not guilty. Well, at that point, we need to make some decisions. We need to decide if we're going to reject this null hypothesis and say that the person is guilty, or if we're going to fail to reject this null hypothesis. And I know that terminology seems a little bit strange, but it's the terminology that we use in statistics. We're either going to reject this null hypothesis, or we're going to fail to reject it, which essentially means we're going to keep it. Well, in this particular case, because it's so unlikely that we would find this evidence if the defendant is not guilty, we're going to end up rejecting that null hypothesis that the defendant is not guilty. And if we reject it, we're essentially saying it's no longer likely, and then we're going to take on the alternative. The defendant is guilty. Well, we're going to do the same type of thing with our data. So let's go through this analogy in another situation where maybe we didn't have as much evidence, just so we can get comfortable with this type of decision making. So let's go through this legal analogy in another type of scenario. So again, we would formulate two competing hypotheses. So somebody is on trial for murder again. And our null hypothesis, as typical, is that the defendant is not guilty. We presume the person is innocent. Our alternative is that the defendant is guilty. And we are going to now look at all the evidence and interpret all that evidence through the lens of the null hypothesis, that the defendant is not guilty. So in step two, we would collect some evidence, like in some type of actual research scenario, but in a legal situation, now we'd be presented with this evidence if we're sitting on a jury. So let's say that the prosecution really doesn't have a very strong case. They present no real witnesses, no fingerprints were at the crime scene, but about the best evidence that they have is that the defendant drives a car that's similar to the perpetrator of the crime. So there were some people who saw a car leave the crime scene, and it turns out that the person who's on trial here drives a similar car. Well, again, now we need to compute the probability of finding that evidence based on our assumption that the null hypothesis is true. So remember, everything is being filtered through this lens that the defendant is not guilty. So what is the probability that this person would drive a similar car? Well, can't you see? I mean, lots of people drive various cars. That's not really very good evidence. The bottom line is it's really pretty likely. It's highly likely that we'd find this evidence just by chance, even if the defendant is not guilty. So just by chance, this person might be driving the same type of car. So in other words, we're still trying to make some sense of that evidence through this null hypothesis, through this understanding that the defendant is not guilty. So what's the probability of finding that the defendant drives a similar car to the person who committed this crime? Well, the probability is pretty likely that we would find that evidence just by chance, even if the defendant is not guilty. So now we need to make a decision. I mean, do we really have enough evidence to rule out our null hypothesis? Do we have enough evidence to overturn our initial assumption that the defendant is not guilty? In this case, we really don't. So we would fail to reject the null hypothesis and conclude that the defendant is not guilty. In other words, we'd keep this. We would retain the null hypothesis. So although you might not think about this process in this way, this is exactly how we make decisions in a criminal case. We first presume that the person is not guilty. We evaluate some evidence. If we find that the evidence is the type of evidence we would expect just by chance, given our assumption that the person is not guilty, then we continue to cling on to that assumption that the person is not guilty. But if we find some damning evidence, like the person's fingerprints are on the crime, then we start saying to ourselves, what's the probability we would find that evidence just by chance? And in that case, the probability would be very low that we would find that evidence just by chance. And then we would have enough evidence to reject our null hypothesis and take on the alternative and say the person is guilty. We are going to do the exact same thing with our data. So as we talk about this and we go through the next several examples, I want you to continue to think back about this legal type of analogy, because that'll help you make sense of what we're doing with our research data. So let's go through an example now that's more closely related to research, and we're going to go through each of those 4 steps. Now, I'm going to just provide you with some information about the probabilities. Later on in the other sections of Chapter 9, we'll be computing those probabilities by hand based on computing z-scores and using our z-table. So first, we're going to state some hypotheses. Let's figure out the situation we have here before we state those hypotheses. And this is just a reminder of the study we talked about doing. So we had a sample of 100 women who were using gender choice, and the sample proportion of the female babies that they gave birth to was 64%. So that'd be 64 female babies out of 100. This P with the little caret on top, you might recall, is the sample proportion. So based on a null hypothesis being 0.50, so remember the null hypothesis is stating that there's no effect. Gender choice makes no difference at all. There's no effect. If that's true and gender choice has no effect, then we would expect about 50% of those babies to be females. So based on a null hypothesis having a population probability of having a female baby of 0.50, we computed a z-score of 2.92. So we took this data and we were able to transform it into a z-score, and let's just say it equals 2.92. So we'll be able to compute that by hand a little bit later on. We already have all the skills to do that, but I've done it for you, and there's our value. And then I looked up the probability of finding that value, and I found the probability of finding that value was very small, approximately equal to this, which would be 13 ten-thousandths. Because remember, if we had a 1 right here, that'd be 1 out of 10, 1 out of 100. This is 1 out of 1,000. This is 13 ten-thousandths. That's a very, very small probability. We could just round it off to like about 1 in 1,000 just to kind of think about it in a more easy way. We're going to test this with what we call an alpha level of 0.01. So as you learned previously, in order for something to be statistically significant, the probability needs to be very small that the results would occur by chance. So what value are we going to use as that chance marker, that borderline value? 0.01, 1% in this particular case. All right, let's go ahead and state some hypotheses. We're going to have those 2 competing hypotheses, our null hypothesis and our alternative hypothesis. So our null hypothesis is that there's no effect, there are no differences, gender choice does not work. If that's the case, then gender choice does not work, and that would mean that the probability, the population probability of having a girl baby would equal 50%. So we're trying to learn with hypothesis testing about this population probability based on our sample data of 100 women. That's why we call it inferential statistics. I'm trying to draw inferences about this population parameter, this population proportion value, based on collecting data from these 100 women. So the null hypothesis is that the population probability of giving birth to a girl baby equals 0.50. Our alternative hypothesis is going to be that gender choice actually works, and it increases the probability of having a girl baby beyond 50%, beyond 0.50. All right, so there we have our 2 competing hypotheses. Step 1 is usually pretty straightforward. Let's talk about step 2. This is where we collect the evidence. So let's assume here now we collected the data from those 100 women. I've already given you a summary of that information. So the data that we've collected for evidence is that the sample proportion, number of babies who were female, was equal to 64%, or the proportion was equal to 0.64. 64 female babies out of 100. Well, at this point we wanted to compute the probability of finding this data based on our assumption that this null hypothesis is true. So what's the probability that we would find a sample proportion of 0.64 if indeed the population proportion is equal to 0.50? So said a slightly different way, what's the probability that from these 100 women, we would find 64 female babies if we're only expecting to find about 50 or 50%? What's the probability that we would find that just by chance if the null hypothesis is true? Remember, all these probabilities that we're talking about and that we're computing are being filtered through the lens of us assuming that the null hypothesis is true. So what's the probability that we'd find this difference between 64 and 50 just by chance? Well, I computed that for us and I gave us that value above. So based on the z-score, the probability of drawing a random sample with a proportion of at least 64% is equal to 0.0013 if the null hypothesis is true. That's a very, very small value. So at this point, we need to make a decision if we're going to reject or fail to reject the null hypothesis. And at this point, because this value is less than 0.01, the result is statistically significant at the 0.01 level. In other words, it's very, very unlikely that we would find these results by chance, and that's what statistical significance is all about. And in this case, the way that we put that to work for us is that we make the decision to reject the null hypothesis. Because our results are statistically significant, we reject the null hypothesis, and then we conclude that gender choice does indeed increase the population proportion of girls who are born, and that it tends to be more than 50%. So we're rejecting our null hypothesis. We're saying we have enough evidence to rule that out. We're taking on our alternative hypothesis, and it says right here that gender choice works. The population proportion of female births is greater than 50%. So this is kind of like saying that we had enough evidence suggesting that the person had their fingerprints on the scene. What's the probability of finding that just by chance? It's very, very low. And because that probability is so very low, we rejected the idea that the person was innocent, and we took on the alternative that the person was guilty. So I hope you're starting to see how that legal analogy works into this hypothesis testing formula that we're working on, this four-step formula, this four-step procedure. So once we go through a few of these, you're going to feel more comfortable with them. I know it's a little bit odd to begin with because you've never done this before. That's the only reason why. It's nothing real difficult. It's just a little odd. So let's go through another example so that it becomes more comfortable to you. So let's go through a very similar example, but in this particular example, we're going to have much less compelling evidence. So let's say now we have a sample of 100 women using gender choice. And the sample proportion of female babies born to those 100 women is equal to 0.52. And because we're using nice numbers like 100, a proportion of 0.52 means 52 babies out of 100. So based on a null hypothesis being 0.50, we compute a z-score of 0.4, which is a pretty small z-score. And we find the probability of finding that value equals 0.34. We want to test this again with an alpha level of 0.01. So that alpha level, again, is telling us how much evidence we need to reject the null hypothesis. So before we even start, let's just kind of look at what we have. We're finding that out of these 100 women, 52% of those babies were female. So the probability was 0.52 of having a female baby. Well, based on the null hypothesis, which states that gender choice has no effect at all, we would expect 50 of the babies to be females. That's not a very big difference, is it? That's not very compelling evidence. That's like trying to convict me of murder just based on saying I drive a similar car to the car that sped away from the crime scene. That's the type of data I would expect to find just by chance. Just by chance, I might drive the same type of car. Just by chance, we might find a difference of 0.52 and 0.50. So when we're just measuring 100 women, just by chance, yeah, I might find a sample of 0.52, even if this particular product does not work. So we've already computed the probability. Let's go ahead and walk through the steps and put it all together. So let's state our hypotheses. So like before, our null hypothesis is always stating that there's no differences, no results, no effects. In this case, gender choice does not work. And that would mean that the population proportion of girls who are born equals 0.50. Half the babies that are born are female. Now, the alternative is the competing hypothesis, and that's that gender choice actually works, and that the population proportion of girls being born to people taking gender choice is going to be greater than 50%. So we have these two competing hypotheses. Now we're going to move on to step 2, where we collect the evidence. Well, evidence has been collected from these 100 women, and it's summarized above right here. And we found that the sample proportion of female babies who were born to those 100 women was equal to 0.52. So we'll just list that there for step 2. We've got the evidence. Step 3, we compute the probability of finding that data based on our assumption that the null hypothesis is true. Remember, we always compute the probability of finding this data based on the idea that the true population value equals 0.50. So what's the probability of finding this difference between 0.50 and 0.52 just by chance? Well, we computed that above. We have that value. Based on the z-score, the probability of drawing a random sample with a proportion of at least 0.52 is equal to about 0.34. So we would expect to find a value of about 0.52 approximately 34% of the time. It's not rare at all. So in other words, we would expect to find this value quite often just by chance, even if this is true. Okay, so that's kind of like saying, I would expect to find that the guy we have on the stand drives a brown car just by chance, even though the guy who committed the crime drives a brown car, and even though we have an assumption that this person is innocent. So just by chance, it's quite likely that we would find that type of evidence. So now we need to determine if we have enough evidence to reject our null hypothesis. Clearly we don't, because we see this probability is not less than our cutoff point. It is not less than our alpha level. So at this point, the probability we figure out is greater than 1%, so the result is not statistically significant. If the result is not statistically significant, we will not reject our null hypothesis. So we will fail to reject the null hypothesis, and we conclude that gender choice does not work, that the population proportion of female babies that are born is greater than 0.50, greater than 50%. So we are retaining or failing to reject this null hypothesis. And again, right here it states that gender choice does not work. The population proportion of girl babies is equal to 0.50 or 50%. So someone might say, like, well, how do you make sense of this difference between 0.52 and 0.50? This is evidence that gender choice works. 52% of these people had a baby. And we'd say, no, that's exactly the type of difference we would expect just by chance, just due to sampling error. We do not have statistically significant results. You did not provide me with enough compelling evidence. All right, well, I hope that this is starting to become a little bit more comfortable as we talk about some of these examples. Let's focus right now on how we set up these hypotheses, because they can be set up in a variety of ways. In this particular situation, we see that we're predicting our results are going to go in a particular direction, that gender choice is actually going to increase the proportion of female babies that are born. We actually call that a one-tailed test. In this case, it's a right-tailed test. I want to make sure you understand those distinctions, so let's focus on that next. Well, one thing you've probably noticed is that these hypotheses that we deal with in step one are always stated in terms of population parameters. We've been looking at the population proportion of female babies that are born. Sometimes we're not dealing with proportions. Sometimes we're dealing with data in which we can compute means. Sometimes we're dealing with a population parameter like mu. Remember, a population parameter is just some characteristic of a population, like the proportion of female babies, or maybe like the mean birth weight, something like that. So we state those hypotheses. So our null hypothesis, as we mentioned before, is that the population proportion of female babies when using gender choice equals 0.50, which would essentially declare it doesn't work. So this null hypothesis is always that initial assumption, and it's always linked to some specific population parameter. So again, I'm trying to learn about that population parameter based on my sample data. I couldn't collect data from all pregnant women who are using gender choice. All I can do is collect data from some sample of those women. And I found 100 women who were going to be using gender choice. Our alternative hypothesis, and you can see a little sub A, oftentimes there's a little sub 1. So if you see an H sub 1 or an H sub A, we're always talking about the alternative hypothesis, is going to be aligned with some type of an effect, some type of difference. This is that the population proportion of female babies being born when using gender choice is greater than 50%. So this is always a competing hypothesis, and it's always listing a different value for the population parameter that we're interested in. So you can see this is a different value because here we're talking about values greater than 50%, greater than 0.50. Let me give you a slightly different version. We could say that for a null hypothesis, again, that gender choice does not work. So the population proportion of girl babies when using gender choice equals 0.50. But it's always possible, too, that gender choice would actually decrease the probability of having a female baby. So if that's what we were predicting, this is how that alternative hypothesis would be listed. The population proportion of female babies when using gender choice is less than 50%. So you can see here again, this value is different than the value listed in the null hypothesis, and the direction is completely different from this right here. And then finally, we could state our hypotheses where the null hypothesis, again, is always stating no effect. And then the alternative hypothesis could be that there's simply some difference. So the population proportion of female babies when using gender choice is something other than 50. And we really don't have any clear idea of which way the data is going to go. It could be that gender choice is going to increase the probability of having a female baby. It could be that gender choice is going to decrease the probability of having a female baby. But we're leaving open the possibility that the results could go either way. So we have some specific names for these types of tests. We call both of these in here one-tailed tests because we are thinking about specific directions for the results. And because in this case, we're predicting that gender choice is going to increase the probability of having a female baby, it's called a right-tailed test. Because when you think about that normal distribution, increases from the middle proportion value of 50% would be on the right side of the distribution. So this is a one-tailed test, which is called a right-tailed test. Another type of one-tailed test is a left-tailed test, because here you can see we're predicting that the proportion of female babies is less than 50%. And in that distribution, proportions that are less than 50%, less than that middle value, are on the left side of the distribution. So it's a left-tailed test. And we would call this a two-tailed test because we're leaving open the possibility that the results could go in either direction. If we do, in this particular situation, reject the null hypothesis and take on the alternative, we could find evidence either way that gender choice either increases or decreases the probability of having a female baby. And we would just simply look at the sample data to figure out which direction is actually the one that provides the most evidence. Let's go through a couple examples, and again, these will feel more familiar to you once we go through a few. So identify the relevant population parameter, state the null and alternative hypothesis, and indicate if the test would be left-tailed, right-tailed, or two-tailed for each example. So let's think about this one. An auto manufacturer claims that a new hybrid car has mean fuel consumption equal to 62 miles per gallon. A consumer group claims that the mean is less than 62 miles per gallon. So let's just say that this is the basis for some type of study. So let's look at our solution here. So first of all, we have to figure out what's the relevant population parameter. What are we trying to learn about? Well, in this case, we're trying to learn about the mean miles per gallon for this particular new hybrid. So it's a mean value. What we're really trying to learn about is some value of mu, the population mean value for these cars. Because remember, all these cars are produced. There's going to be some variability from one car to the next. I'm trying to learn about what's the population mean value for all of these cars when it comes to their miles per gallon. And of course, in some type of research study, we would just collect data from a sample to try to learn about that population. So let's set up the hypotheses. This says that the consumer group claims that the mean is less than 62. Remember, the null hypothesis claims that there's no difference, no effect, no types of differences at all. So our null hypothesis is going to be very straightforward, and that is that the population mean miles per gallon for this new hybrid is equal to 62 miles per gallon. Now, these guys are predicting that the mean is going to be less than 62. So we can see here that our alternative is going to be that the population mean is less than 62. So it's relatively straightforward. And this, because we're predicting scores less than that middle value, less than that mean value based on the null hypothesis, this would be a left-tailed test because values less than 62 are on the left side of that distribution. So the hypothesis test is left-tailed. Let's go through another example. Identify again the relevant population parameter, state the null and the alternative hypothesis, and then indicate if we'll be using a left-tailed, right-tailed, or two-tailed test. The Ohio Department of Health claims that the average stay after childbirth in Ohio hospitals is greater than the national mean of 2 days. So already we can see that we're dealing with a mean, we're not dealing with percentages. And what we're looking at specifically is we're trying to figure out the population mean stay in the hospital for women in Ohio. Okay, so that's what we're trying to learn about. The relevant population parameters, the population mean, mu, stay in a hospital after childbirth in Ohio. Well, let's think about our hypotheses. Remember, the null hypothesis is that there are no differences, there's no effect. And in this case, we see that the national mean is equal to 2 days. Well, The null hypothesis would state that Ohio is no different. Women in Ohio spend the same amount of time as people in the nation. So our null hypothesis would be that the population mean number of days that women stay after giving birth to a child is equal to 2 days. Now let's think about our alternative. The Ohio Department of Health claims that the average stay after childbirth is greater than 2 days, so they're staying longer. So our alternative is going to be that the population mean is greater than 2 days. So again, we can see that this is a one-tailed test. And because we're predicting here with our alternative hypothesis that the women in Ohio are staying longer than 2 days, we're talking about a right-tailed test because values greater than 2 days are on the right side of the mean in that distribution. So in this case, the hypothesis test is a right-tailed test. Let's go through another example. We want to make sure that we can nail this. Identify the relevant population parameters, null and alternative, and whether we're dealing with a left, right, or two-tailed test, just like we did before. So a wildlife biologist claims that the actual proportion of female African zebras is different than the accepted proportion of 50%. So let's just assume in that community of biologists, they believe that about half the zebras are female and half are males. But this particular wildlife biologist claims that the actual proportion of female zebras is different from that value. Can you see how this particular example is a little bit different? This particular biologist who is doing this study is not necessarily claiming that there are fewer females or more females, but just that he thinks there's some type of difference. All right, well, let's set up what we're dealing with. So first of all, what's the population parameter of interest? Well, we're trying to learn about the proportion of female zebras in that population. So now we're dealing with the population proportion, not a mean anymore. So the relevant parameter is the population proportion, and we just use a P to represent that, of female African zebras. Now, our null hypothesis always states that there are no differences, no effects. So what's the general accepted value? 50%. So our null hypothesis is that the true population proportion of female zebras is equal to 50%. Now, our null hypothesis is going to be that that value, that true value, is something other than 50%. We're not necessarily sure if it's greater or less. We don't have any clear predictions, but we think it's something other than 50%. So that's how our alternative hypothesis would be listed in this case, that the population proportion would be something other than 50% regarding the number of female zebras. So in this case, you can see that we're dealing with a two-tailed test. This is a two-tailed hypothesis test. Let's look at another example. Interpret the possible outcomes for this hypothesis test. So now we're going to take this a step further, and let's actually interpret what it would mean to reject the null hypothesis or fail to reject the null hypothesis. So this is actually what we do in step 4 when we interpret our results. So let's go ahead and make sure we understand how to do that. An auto manufacturer claims a new hybrid car has a mean fuel consumption of 62 miles per gallon. So this is the same example we looked at before, but now let's interpret the results, how they can come out. Remember, there are 2 ways that they can come out. We're either going to reject this null hypothesis and take on the alternative, or we're going to fail to reject that null hypothesis and we're going to keep it. So let's see what we would have here. Based on rejecting the null hypothesis, that would mean that we have evidence that the population mean miles per gallon is less than 62. Because if we reject this value right here, if we reject it, we're then taking on the alternative and we're saying that this is true. So the population mean fuel consumption for this new hybrid car is less than 62 miles per gallon. Well, now let's see how the results would look if we failed to reject the null hypothesis. If we fail to reject the null hypothesis, that means we do not have sufficient evidence to conclude that the population mean miles per gallon is anything less than 62. So we didn't have enough evidence to reject it. If we're keeping it, if we're failing to reject it, we're saying that the population mean mileage for this car is equal to 62 miles per gallon. So you see, it's relatively straightforward. All we really need to do is look at what did we write down for these hypotheses and then interpret the results just by kind of reading it back. That's why it's so important that we got this step right. Let's go through another example. So let's interpret the results for the Department of Health study regarding the average stay for women in Ohio. We knew that the national average was equal to 2. The Ohio Department of Health believes that women in Ohio are staying more than 2 days. So let's see here. If we are going to reject the null hypothesis, what would that mean? Well, if we reject the null hypothesis, we're taking on this alternative. Remember, we're rejecting this and we're taking on this to be true. And this literally says the population mean number of days that women in Ohio stay in the hospital after giving childbirth is greater than 2 days. Now, let's say that we didn't have enough evidence to reject the null hypothesis. So if we fail to reject the null hypothesis, that means we're keeping this. That means we still think that this is true. And in this particular case, we'd have insufficient evidence to conclude that the average number of days that women stay in the hospital after childbirth in Ohio is anything other than 2. So essentially we're saying we believe the population average number of days that women stay in the hospital after giving birth in Ohio is equal to 2 days. So the interpretation is really very straightforward once we determine if we're going to reject or fail to reject. We just look at what those hypotheses are. Let's go through that final example there before we move on to a new one where we put it all together. So again, let's interpret the possible outcomes. This had to do with the female zebras. This was a test that was non-directional. It was not a one-tailed test. This was a two-tailed test. We did not predict the direction of the results. So let's say that we do reject the null hypothesis. If we reject this null hypothesis and take on the alternative, we're saying that the true proportion of female zebras is something other than 50%. It's not equal to 50%. If we fail to reject the null hypothesis, that means we're keeping this. That means this is still the best explanation, the most probable. And here we're saying the probability or the population proportion of female zebras is equal to 50%. All right, so hopefully by now you see that that's pretty straightforward in terms of the results. Let's go through an example where we kind of put things all together. We're going to go through a couple of these, and you're going to see now how we kind of put it all together with interpreting our results and listing these hypotheses. So let's look at this one right here. Americans drive about 12,000 miles per year. A rental car manager suspects that his fleet travels more miles than that. So he can't get data from the entire fleet, but he samples 225 cars and finds that the mean miles traveled for those cars is equal to 12,375 miles per year. So there's a difference between 12,000 and 12,375, but we don't know if that's statistically significant or if that's the type of difference we would expect just by chance, just due to sampling error. If we assume that the fleet mean is equal to the national mean, remember that's what the null hypothesis is all about, always assuming that there are no differences, no effect, then the probability of selecting this sample and finding this mean just by chance is equal to 0.008. We would expect this only 8 times in 1,000 just by chance. Well, let's say our alpha level for finding statistical significance is 0.01. Do we have statistically significant results? Let's go through the different steps and make a decision based on the information we have here. So let's state our hypotheses. Remember, our null hypothesis states no effect, no differences. That would mean that our null hypothesis is stating that the population mean miles traveled per year for the fleet is equal to 12,000 miles a year. Remember, we're trying to learn about a population that we did not measure. So in other words, we're trying to learn about the population that's represented by this sample of 225 cars. In other words, we're trying to learn about that fleet. So the null hypothesis states that the average miles driven by the fleet is equal to the national average. Our alternative is that the mean miles driven by the fleet is something greater than 12,000 miles. And the reason why we're listing it this way as a right-tailed test is because the rental manager suspects that his fleet travels more miles than that. All right, so we're putting our alternative hypothesis so that it's consistent with the rental manager's suspicions. So then we collect some evidence. Well, I've already provided you with the evidence. Based on this sample of 225 cars, we find that the mean miles driven is equal to 12,375. So we're just going to list that right down here just to be complete. Now we're going to compute the probability of finding this data just by chance based on our null hypothesis. So what's the probability of finding a mean of 12,375 if the true population mean is equal to 12,000? What's the probability of finding a sample mean like that just by chance? Well, I computed that for us right over here. So we're going to be able to do that on our own soon, but here I've provided you with the probability of finding that difference just by chance. So if the population mean for the fleet is actually equal to 12,000 miles, remember that's the null hypothesis. We're always computing these probabilities based on the null hypothesis being true. So if the mean for the fleet is actually equal to 12,000 miles, then the probability of selecting a sample with a mean of at least 12,375 would only be 0.008. So we would not find that very often just by chance. This is kind of like finding my fingerprints on that murder scene. If my fingerprints are on that murder scene, it's very unlikely that we would find that just by chance. And you would then rule out your null hypothesis that I'm innocent, and you'd take on the alternative that I'm guilty. Well, that's what we're going to do right here in step 4. Because this value is very small, and because it's smaller than our alpha level, that means we have enough evidence. So we met our criterion value. We have enough evidence. So in this case, the probability is less than 0.001. So the result is indeed statistically significant at the 0.01 level. So we're going to reject the null hypothesis and conclude that the population mean mileage for the rental fleet is greater than 12,000 miles a year. And we can make sense of that very easily by literally rejecting our null hypothesis and then taking on that alternative. And what does that alternative say? The population mean, miles driven for the fleet, is greater than 12,000 miles per year. So hopefully this is starting to become a little bit more comfortable for you. Let's go through another example. The only way that it's going to be comfortable is if we go through several examples. And it's very important that this does become comfortable because we're going to be learning here a very simple test, a z-test. That's what we're talking about right here. Z-test is very simple, but it uses this very powerful 4-step procedure, and this same 4-step procedure is used in essentially all inferential tests that you're going to encounter. So once you learn this one, you've learned a lot about many different tests that are out there. So it's very important that we have a good base. Let's go through this example. You suspect a coin lands more tails more than heads, so you toss the coin 100 times to test it. You get 40 heads and 60 tails. The probability of getting 40 or fewer heads in 100 tosses of a fair coin is equal to 0.0228. So it only happens about 2% of the time just by chance. Is the coin biased against heads? In this case, let's change that alpha level to a 0.05 just so we get some experience using different alpha levels. Remember, as I mentioned, different disciplines require different amounts of evidence. So in like psychology, sociology, social work, nursing, in many different disciplines, the typical alpha level is 0.05 for the results to be statistically significant. And we can see, we found that these results are very unlikely to happen by chance. Well, let's go ahead and fill in everything so we can more formally make decisions. Let's state our hypotheses. So our null hypothesis is that the population proportion, when we flip that coin for when it comes up heads, is going to be equal to 0.50. Because the null hypothesis is that it's a fair coin and that it should come up about 50% of the time heads, 50% of the time tails. Now, when we look at the alternative, we're going to see if there are some departures from that. So this says you suspect that the coin lands tails more than it does heads. So here we're seeing that we think the probability of heads is less than 50%. So this is another one of those one-tailed tests. And in this case, it's a left-tailed test because we're predicting that the proportion in the population proportion of heads would come out less than 50% of the time. So if we're able to keep repeating and repeating and repeating, flipping this coin less than 50% of the time, it would come out heads. Well, we collect some evidence. We already did. We flipped that coin 100 times, and we found that it came up heads 40% of the time. So that's a pretty big difference there, 40% when we're expecting 50%. And in step 3, we're going to compute the probability of finding that result just by chance. So if it is true that that coin comes up heads 50% of the time, what's the probability that in these 100 tosses, we'd find out that it comes up only 40% of the time? What's the probability of finding this data just by chance if this null hypothesis is true? Well, the probability is equal to 0.0228, so it happens about 2% of the time. So if we assume that the coin is fair, and remember that's what we're always doing, we're always computing these probabilities by looking at it through the lens of the null hypothesis that this is true. So if we assume that the coin is fair, then the probability of finding a sample proportion as extreme as 0.40 is equal to 0.0228. Well, that meets our cutoff point. That is less than 0.05. 0.02 is less than 0.05, so we have statistically significant results. So the probability is less than 0.05, so the results are statistically significant at the 0.05 level. What does that mean we're going to do with our null hypothesis? We're going to reject it. We're going to reject that null hypothesis. So we reject the null hypothesis and we conclude that the proportion of times that we get heads is less than 0.50. So we reject the null hypothesis and we conclude that the population proportion of times that we get heads is less than 50%. So there is some bias against heads. So we're going to rule out, reject this null hypothesis, and then we're going to take on or approve the alternative. And that is that the population proportion of times that we find a heads result is less than 50%. Let's go through just one more example. Let's go back in this next example and change our alpha level to 0.01. So let's just assume that we're in a discipline that required a little bit more evidence to find statistically significant results. And let's look at this exact same example that we just dealt with. This time, though, we have an alpha of 0.01. So by going through this example with these two different alpha levels, and we can see here our evidence isn't going to be enough to meet our criterion. We're not going to have enough evidence to say we have statistically significant results. By going through this example this way, you'll be able to see with two of exactly the same examples how the results can go one way or the other based on if we have enough evidence to find statistically significant results or not. So again, let's state our hypotheses. They're going to be the same. Our null hypothesis is that the population proportion of times that it comes out heads is equal to 0.50. The alternative is that it's going to be less than 50%. We collect evidence. We already did. We found that 40 times it comes up heads. So the sample proportion of times that our coin came up heads was equal to 0.40. So we compute the probability of finding that just by chance. We did that already. The probability was equal to 0.0228. So it's relatively unlikely that we would find that data just by chance. However, it did not provide us with enough evidence. It's not rare enough. Well, in this particular case, because we need quite a bit of evidence and because we did not find enough evidence, we are going to fail to reject the null hypothesis. So the probability is greater than 0.01, so the result is not statistically significant at the 0.01 level. We fail to reject the null hypothesis, and we conclude that the population proportion of times that that coin is going to come up heads is equal to 0.50. So in other words, we're retaining or failing to reject that null hypothesis. We still believe now that the population proportion of times that that coin will come up heads is equal to 0.50. All right, so those last two examples give you good examples of how it looks when we have statistically significant results and when we do not. All right, I know that was a lot to take in, and these really do require practice, and that's why we're going to take this slowly in class. So be sure that you study and you do some of the practice problems, and if you have questions, you bring them up in class. That, my friends, was the key content from this particular section, and for now, that is all.